Okay, so welcome back. So if you recall, in our last class, we ended up in uh, equation of a straight line. So to be precise, we are trying to do vector equation of a straight line. Okay. So what I'm going to do, let me just try to recall what we did and how did we arrive at the equation of a straight line. I'm going to do it quickly. So what we did, suppose I'm considering the three-dimensional space, three-dimensional space. So then I was considering the equation of a straight line, and what information we have that the straight line it passes through a fixed point, say P naught, X naught, Y naught, J. Okay, and another information that we had in hand was that the straight line it is parallel. It is parallel to a given vector. And remember, although we didn't say that the vector, I mean, basically we didn't say anything about the location of the vector, okay? But if you recall, we took it in such a way that it started at the origin. So now the point is, I mean, it doesn't necessarily have to start at the origin, but you already know that. I mean, by parallel displacement, we can always make any vector, I mean, originating in the origin. Okay, so that vector, suppose it was given by V bar, if you recall. Okay, and we assume that the components of B, it was A, B, and C. Then what we did, always remember the general methodology is that what you have to do in this straight line, let me call it L straight line. I am going to take a variable point P, and then I am going to join those 2 points to the origin. Okay, 2 points to the origin. I am going to call this fixed vector as R dot and this variable vector as R, right? And then from this figure, you know that your R is simply R dot plus this P naught P, right? Again, since P naught P is parallel to this given vector V, so it must be a scalar multiple of V, and that we take as TV, okay, where T is a scalar, it is a real number, and this gives me the vector equation of the straight line. Okay, and we also discussed that depending upon the value of T, you will be able to find out the location of a point on the given straight line. Okay, for example, if T was greater than 0, so definitely I am going to find that particular point to the right of P naught, and if T is less than 0, we are going to find that point to the left of P naught in this straight line L. Okay, so this is what we did in our last class. So now, if I decompose this vector into its components, so then what we will get from this equation, we get that your x, y, z. So this is equal to your x naught, y naught, y naught, z naught plus d, a, b, c. Okay, fine. And this can be written as x equal to x naught plus nt, y equal to y naught plus bt, and j equal to j naught plus c. Okay, and if I consider this set of equations, so let me call it A. Okay, so this is called the parametric form of the equation. Parametric form of the equation of the straight line. Okay, this is called the parametric form because they are values of the parameter t. Fine. Yes. So, thanks. So now let us see what we can get from here. Okay. So now if you look at equation A, so then you will see that if I try to eliminate t from equation A, so then this is going to be of this format. this is going to be of this form. Okay, and you can see that there is some symmetry about all three ratios, isn't it? So that is why this particular form of the equation is straight line, it is called the symmetric form. Symmetric form of the equation of the straight line. Okay, so basically, I mean, if you look at the symmetric form, what you will see the point through which the fixed point through which the straight line passes through. Okay, and the straight line. Another thing, this is very, very important. Please look carefully. I mean, if I look at the denominator in all those three ratios, so those, I mean, come out to be your A, B, and C. And what were they? They were nothing but the components of the vector to which the straight line is parallel to. Okay, so now let me I mean, spend a little time on that again. Okay, so now let me try to get back to what we done there in this direction angles and direction cosines. Okay, so if you recall, like the direction cosines, or first the direction angle of a vector, was nothing but the angles made by this vector, which x, if it is alpha, which y, if it is beta, if gamma, if it is with z axis. That is what the vector makes with x, y, and z axis. Okay, and we call cos alpha, cos beta, and cos gamma, right, as the direction cosines. Okay, so now again you can see, I mean, we found out that this direction cosines, are intrinsically linked to the, I mean, say, suppose the endpoint is P here, okay, and if it's, I mean, coordinates where, say, what should I take? Let me take it as some maybe, okay, ABC, no problem about this, ABC. So then, what was happening, if you recall, ABC, it was simply your we had this relation, isn't it, if you recall? Fine? Yeah. Okay, so then, now, what is happening out here? So these were called direction cosines. Okay, so basically, now see, if you consider this situation to this one, okay, so here I have this vector v, and you know that the vector v is parallel to the given straight line, right? So that means this straight line is also going to make angles alpha, beta, and gamma with the axis if the vector v makes those angles. Is it okay? Fine. So that means if I try to find out the direction cosines of this straight line, so then what it will be? It is going to be the same as this. Okay. So now, say, suppose if I shift this straight line to the origin, if I follow the same procedure, so then if I consider say a portion of this straight line, and if I take out a vector out of it, so then obviously that is going to be some scalar multiple of this ABC, right? So here we have taken it as t into ABC. So t into ABC. So now if you look at this, you will see that both of them has the same direction cosines, right? But this multiple, it is different. Okay? So that is why if I want to relate this ABC, which are nothing but a component of the original vector V bar, okay? So that means it bears a ratio with the vector parallel to it, okay? And if I want to, relate them to the direction cosines, that is why this A, B, and C, they are called the direction ratios. They are called the direction ratios. Okay, fine. So A, B, C, this A, B, and C, they are also called direction ratio. And now you may be asking me why it is so important. Why it is so important? Because if I consider say any straight line passing through the point P naught, okay, and which is parallel to L, right? Then what is going to happen? Their direction cosines are going to be the same. Okay, fine. Direction cosines are going to be the same. Now, if you have another straight line passing through P naught, the parallel to L, so then its equation is going to be something like this. Its equation is going to be something like this, right? And then we can simply adjust it like this. Okay, so basically, two parallel straight line passing through the same point. Basically, what is happening? They are the same straight line. Only thing is that in terms of the vector equation, what we can do, we simply made, based on that, parameter t, okay, you are going to consider the variable point p. That's it. So I'm going to do another equation over there. What I'm trying to tell is going to be more clear to you. Okay. Okay. So now let us try to find out. Say, try to do one exercise. Say, suppose we want to find out the equation of a straight line passing through this, okay, and which is parallel to I plus 4j minus 2k. This is straightforward. Okay. So basically, what is happening here? The fixed point P naught is this. Okay, and this is the vector to which the straight line is parallel to. So your V is simply from here 1, 4 minus 2. Okay, fine. So that means the equation of the straight line is going to be your R equal to R naught. That is simply 5, 1, 3. Okay, and then P into 1, 4. This. Okay. Now, if you want to write it in symmetric form, it's pretty straightforward. R has the component your x, y, and j. R has the component x, y, and j. So that is why it is going to be x minus 5 by 1 equal to y minus 1 by 4 equal to j minus 3 by minus 2. Okay.
Yes.
Right? Okay. So now, suppose you are told to find any two other points on that straight line. Okay. So now here this equation is what? Only thing is that this is what? This is your 5, 1, 3, and this B is simply given by 1, 4 minus 2. Okay. So now, as I have told you, depending upon the value of t, you will be able to find out all the points lying on the straight line, isn't it? Fine. Okay. So you know that if t is positive, then any point on the straight line you will find to the right of p naught. If it is less than 0, you can find t toward the left of p naught. Okay, so we can take t equal to 1. We can take t equal to 1. So here, if we take t equal to 1, so then this r we are going to get as 6, 5, 1. Isn't it? Fine. So
Yes.
we will take a point somewhere here. Right. So similarly, if you take t equal to -1, you will get another point. Right? So you simply vary t and you are going to get whatever number of points you want on that string. Okay? Fine? So now what I'm going to do this equation, that is vector equation, firstly, then we can compose it into symmetric and parametric form. Don't worry about it. So, equation of a straight line passing through 2 points. Passing through 2 points. Okay, fine. Now, see, from the earlier example, you have seen that the information that we had in our hand was what? There was a fixed point P naught, and there was a fixed vector V bar to which the straight line is parallel to. Okay, so now we don't have this information. We don't have information about this vector. Okay, but instead of that, what is happening here?
Sir, maybe you can switch off the lights.
Oh,
Reflection is coming. Yeah,
Let's find
it's
out.
fine. Yeah.
So, what is happening here? Now, we are giving 2 points. Say P naught, this is say X naught, Y naught, Z naught. Okay, and then suppose we have another point, say P1, say X1, Y1, Z1. So we don't have this information, but we have this extra information. Okay, so now what we are going to do with this extra information, we will find out a vector parallel to V curve. Okay, see, basically what we have to find out. We have to find out a vector to which the straight line we are trying to find the equation of is parallel, isn't it? Now, if I consider P naught, P1, this vector lies on the given straight line, isn't it?
Yes, sir.
Fine, isn't it? So that means this vector itself is parallel to the given straight line. Fine?
Yes.
Is it okay? So
Yes.
that case, we have found out our P. So what we are going to do, as before, I mean, so this point is P naught, X naught, Y naught, Z naught. So suppose this point is P1, X1, Y1, Z1. So what we are going to do, we are going to take a variable point here, say here. This is X, Y, Z. Okay, so you may be asking me why I am always taking this point beyond these two. I could easily take this point P here somewhere also. It is not going to matter. Let me guarantee you. Okay, so and then as before, what I am going to do, I am going to join this, variable point and this fixed point with O. Okay, and then from this figure, you can see that your your OP, this is equal to OP naught plus P naught P naught P. Fine.
Yes, sir.
Is it okay?
Yes.
And OP, simply I am going to call it as
R.
R, and then this is R naught, and then you can see that this P naught P, it is simply a scalar multiple of P naught P1, right? So that is why I can, and so P naught P, so this P naught P simply is a scalar multiple of this scalar multiple of P naught P1. So that is why I can take it as T into P naught P1, right? So now if I think about P naught P1, what is this? This is nothing but your R1 minus R1, isn't it? If you, so this is R1, right? This vector is R1. So this vector is going to be R1 minus R0. Okay, fine. So that is why this can be finally written as your 1 minus T R0 plus T R1. T R1. Okay, and of course T is a real number. Okay. So now let me pose a question to you. Say, suppose if I try to find out the equation of the portion of the straight line, that lies between P1 and P. So basically, we are trying to find out the equation of the straight line in such a way that a point always lies here. A point always lies here in this portion. So if your P is here, so then can you tell me what must be the value of T?
T must be negative.
No. If T is negative, then it is going to
Yeah. Beyond left side of the P.
P naught. But I want it to lie between P naught and look at this. Look at this one.
T must be equal to 1.
0 and 1.
Yes.
It must lie between 0 and 1. Okay, if you want to find out a point between P naught and P1, right? Because if it is 0, T is equal to 0, then the point is P naught itself.
P naught.
Right? And if T equal to 1, the point is P1 itself. So that is why in many books, they will try to give you the equation of only the portion P naught P1. Okay, so in that case, your T is going to lie between 0 and 1. Okay, fine. Let me have some water, and after that I'll come back. So I can give you an exercise where I'll tell you to find out the vector equation of a straight line passing through 2 points, where the 2 points are given. So then simply plug it in this problem. So I'm not going to do that. I mean, you guys are going to have enough examples in your tutorial sheet, and I have already given you I have already given you the Stewart book, uploaded the Stewart book in my personal website. I think I have uploaded it in this class material section also for this particular class. So there are many exercises there. Please do as many as you can. Okay, fine. So now, let me. Fine. Okay, fine. So this is about vector equation of the straight line. So now let me come to equation of a plane. Let me come to equation of a plane. Okay, fine. See, what was happening earlier. Now, when we were trying to find out equation of the straight line, the information that we needed was a fixed point, right? And what? Like say another vector, another known vector to which the straight line is parallel to, right? So basically, the another vector which is known, right? That had given me the direction of that straight line. Fine? Is it clear? Okay. Now, when we come to the question of finding the vector equation of a plane, again, what we are going to do, definitely we are going to take a point lying on that plane, and that is going to be my fixed point. But what about the direction? Okay. Now, because I can have infinite number of straight lines lying on that particular point, right? And then what is going to happen? All those lines, they can have, I mean, different directions, right? So, but we need to find a unified, I mean, common direction, which is going to give me some idea of finding the equation of the plane. So here, what is done here? Say, suppose this is my plan. Say this book. Suppose this is a plan. Then you will see that if I consider a normal to the plan, the scale that I'm holding, it is, you may consider it to be a normal, right? So then, and again by parallel displacement, if you know about a normal to a particular point to the plan, by parallel displacement at any point, you can make that normal to be a normal to any point on that plan. Okay, so that means what we are going to do here, the information that will be given to you in order to find out the vector equation of the plan is that you will be knowing a fixed point lying on the plan, and you will be knowing the normal. You will be knowing about the normal to the plan at that point. Okay, so based on that, let us try to find out the vector equation of a plan, and which we will convert it into a scalar equation. Okay, right. So suppose this is my plan. The draw the axis x, y, j, draw the axis, and suppose this is my fixed point P naught, x naught, y naught, j naught. Okay, and suppose this is the normal to the plan, which I am going to designate as n bar. Okay, so as before, what we are going to do, I am going to take a variable point that lies on that plan. Is it okay? So suppose that variable point is suppose that variable point is p. Excellent. Okay, and then as before, we are going to join the origin to those 2 points, P naught and P. So this one. Suppose this one. Okay, so then if I call this as r naught and this vector OP as r, okay, so then you know that this plus this is this, okay, and so this vector is nothing but what? R minus r naught. Okay, fine. So now from here you can see that because now r minus r naught is a vector lying on the plan. Say suppose this is this pencil is a vector lying on the plan, right? So then I have this normal, right? So obviously this vector is going to make an angle 90 degree with the normal, right? So that means what is happening out here? What is happening out here? Obviously, the vector P naught P, it is perpendicular to this. Okay, and P naught P, that is R minus R naught, which is perpendicular to N. So this point and this angle is 90 degree. This angle is 90 degrees. Okay, so from the property of dot product, what we get R minus R naught dot N to G, right? Okay, and if the components of N, I mean, if it is given as ABC, then from here what we get x minus x dot, y minus y dot, z minus z dot, ABC, this is equal to G. Okay, so that means okay, right? So this is the equation of a plan passing through the point x naught, y naught, z naught, and A, B, C are the components of the normal to the plan. Okay, so now I would like to tell you another thing. See, obviously, once you simplify it, this can be decomposed as ax plus by plus cy equal to 0. Okay, so whenever you see an equation like this, from here you should be able to tell immediately that the coefficients of x, y, and z, they are going to denote the components of the normal to that plan. Okay, which we are going to make use of in order to solve problems. Is it okay? Right. So now the next question is, say, suppose I want to find out the angle between two plans. My situation is going to something like this. Say, suppose I have this plan, I have another plan, okay, and I want to find out the angle between these plans. Okay, fine, here. Okay, so how we go about it? Any idea? Yes? It is obvious. What you do, you simply draw normals to those two plans, right? Okay, and then the angle between those two normals is going to give you the angle between these two plans. So let me show you them in slides. So here. The okay. So now we are going to do that example later on. See here, isn't it? So these are the two plans. Okay, this one is a plan, and you can see that they are between x theta. So now if you draw normal to the plans, so this plan you draw the normal n1 and the other one you got from 2. So then you can see that the angle between these two plans is nothing but simply the angle between the plans. Okay. So now meanwhile, let me just note down those 3 points. 1, 3, 2, 3 minus 1, 6, and 5. So the the problem that we are going to do now. So what you have to do that you are given 3 points, like those 3 points you can see next to that. Okay, they lie on a plane. So what you have to do, you have to find out the equation of that particular plane on which those 3 points. Okay. See what we have. Suppose those points are say P naught, Q naught, say R naught. So now what we have, in order to find out the equation of a plane, what we need? We need a fixed point, right? Lying on the plane. We are given 3 points. We can choose any one of them. Okay. Let me choose this one, P naught. Let me guarantee you that. I mean, whether you take P naught or Q naught or R naught, eventually you are going to get the same equation of the plane. You don't need to worry about it. You can try this. Okay, fine. So I have one information. Okay. So the next information is that. I need what? The components of the norm. Components of the norm. Okay, fine. Say now, how are you going to find it? Say suppose your plan is nothing but the plan of this blackboard itself. Okay, I am considering this to be my plan, which is nothing but the blackboard. Okay, and I have 3 points lying here. Say P naught, Q naught, R naught. Okay, fine. So now I need a normal to be planned. Any idea how we can do that? Okay, let me tell you. You will see that it's going to be very, very easy. Okay, see, I can find out any 2 vectors out of these 3 points. Okay, say suppose I am considering this vector P naught Q naught and P naught R naught. Okay, fine. So then what is going to happen? Now, see here, your P naught Q naught is going to be the vector 3 minus 1, 2, minus 1, minus 3, minus 4, 6 minus 2, 4, and P naught R naught. This is going to be 5 minus 1, 4, 2 minus 3, minus 1, 0 minus 2, minus 2. Am I okay?
Yes.
Fine. So now you have found out these 2 vectors lying on the plane. So now if I consider the cross product of P naught Q naught and P naught R naught, what property are they going to have? I am going to get their cross product as another vector which is perpendicular to which is perpendicular to both those vectors. Isn't it? Right? Since both those vectors lie on a plane, so that means their cross product is going to be a normal to the plane on which they lie. Is it clear? Yes? Is it clear?
Yes, sir.
Okay. So that is why I am going to take my n as the dot product of these 2 vectors. 2 minus 4, 4 cross 4 minus 1 minus 2. Okay? And then okay, so then this is going to be 4 to the 8, 8 plus 4, right? Right, I, then minus 2. sorry, 2 into minus 2, that is minus 4, minus 16, that is minus 4 minus 16, that is 20, minus 20. So this minus and this minus, this makes it plus 20, right? Plus 20j. And then minus 2
minus
plus 16, that is 14,
14.
right? So plus 14, right? Plus 14k. So I have found out that normal. Okay. So what we have now? So now you can take any of those three points. Okay. So if I take P naught as my point to which which is a fixed point line on the plan, and I know the normal. It has components your 12, 20, 14, 12, 20, 14. So then I know the equation of the plan passing through this point is given by 12 into x minus 1 plus 20 into y minus 3 plus 14 into z minus 2. This is equal to 0. So what we can do in our next line, this is a multiple of 2. So 6x minus 1 plus 10y minus 3 plus 7 z minus 2 equal to 0. This means 6x plus 10y plus 7j. This is minus 6. This is minus 30.
Minus
This
14.
is minus 14. This is equal to 0. This implies 10y plus 7z. So
50.
56, 50, yes. 50. So this is my equation. Okay. So if you, if you take Q naught, if you take R naught, whatever point you take, even you can consider another combinations of vectors from those 3 points. Okay. And eventually, whatever you take, after simplification, you will see that you are going to arrive at this equation. You are going to arrive at this equation. Okay, fine.
So it means if we take the point Q naught, then we have to take the normal vector corresponding to that point.
Not necessarily. Not necessarily.
So we can work out with same normal vector also.
Yeah, yeah.
So in this case, the constant might be different.
Because see, whatever normal you are going to get, say suppose I take say combination. Suppose I take combination this and this. Okay. From here I am going to get a normal, right? The normal, the normal may be different from whatever I have got at this point. Okay. But since they are parallel, they are going to be scalar multiple of each other. Isn't it? So eventually after simplification, that scalar multiple will come out, right?
Okay, okay.
Isn't it? So eventually you must get the same equation, whatever combination you take. Okay, fine. Just a minute. Yeah, you should get the same answer. You check at one. Okay. How much time do I have? So I'll take another interesting example. So I'm taking another example. Here, the first question is finding out the angle between these two planes. Z equal to 1 and x minus 2y plus 3 z equal to 1. Okay, the first question is finding out the angle between them. Okay, I'll come to the second question later. Let us try to find out the angle between them. And you already know that, right? The angle between, two planes is nothing but the angle between their normals, right? Angle between the normal to those planes. Okay. So if I assume that your N1 is a normal to this plan and N2 is a normal to this plan, so then you know that their components are simply this. As I have told you that if the equation is of the form ax plus by plus cz equal to d, then immediately you should identify that a, b, c are the components, right, of the normals. So this is going to be 1 minus 2, 3. Okay, fine. So then what we are going to do, if we assume that the angle between these two planes is theta, so then theta is the angle between those two normals, right? So if I use this formula of dot product, fine. So then from dot product formula, this is going to give me what? 1 into 1 plus 1 into minus 2 plus 1 into 3. So that means 1 minus 2 plus 3. And this is going to give me what? Square root 3, 1 square, 1 square, 1 square. And then this is 1 plus 4 plus 9. 9 plus 4, 13 plus 1, 14. Cos theta. So eventually, from here, I will be able to find out this to be okay. So this is the way we are going to find out the angle between two planes. Okay, that was my first question. Okay, the second question is a bit tricky. Second question is a bit tricky. So what is the second question? What is going to happen? I mean, if we consider two planes which are not parallel to basically, their direction ratios are not proportional to each other. Right? The direction ratio, or no, let us not look in direction ratio, because direction ratio is related to a straight line only. Okay, so their components are not scalar multiple of each other. Okay, so then the planes are not parallel, right? If the normals have different directions, they cannot be parallel. Okay. Fine. So if two planes are not parallel, then what is going to happen? They are going to intersect in a what? Two planes are going to intersect in a line.
Yeah.
Right? Okay. So the next question is, find the symmetric equation of the line of intersection of the two planes. That is one. The next question. Okay, so it is something like this. Say, suppose I have a plan, I have this plan, and suppose I have another plan like this, right? So then they are going to intersect in a line. They are going to intersect in a line. Okay, so now my job is to find out this equation of this straight line. So suppose this is my plan, I mean pi 1 given by this x plus y plus z equal to 1, and suppose this is pi 2, this plan, this is given by x minus 2y plus 3z equal to 1. Okay, right? Now I need to find out the equation of this straight line L, which is nothing but their intersection. Okay, fine. So if you recall, in order to find out the equation of the straight line, what we need? Firstly, I need a fixed point. I need a point lying on that line. Secondly, what I need, I need the direction ratios. I need the direction ratios of the line. Okay, fine. So what I will do, I will first try to find out the direction ratios of the line. Okay, so you may be thinking like this is very difficult, but just some a simple logic that we are going to use it here. Okay, geometry to use it, you'll see that it is pretty straightforward. Okay, so now what we have assumed that N1 and N2 are the normals to those planes. Fine?
Yes.
Here. So now you know that the straight line L, it lies on the plane pi 1 as well as on the plane pi 2, right? Because N1 is normal to pi 1, so that means that straight line L must be perpendicular to N1. Is it okay?
Yes.
Similarly, N2 is a normal to the plane pi 2, on which again the line L lies, right? So that is why what? L must be perpendicular to N2 as well, and vice versa. Isn't it?
Yeah.
So what we have found out that L is perpendicular to N1 and L is perpendicular to N2 as well. Okay? On the other hand, by the cross product of two vectors, if this cross product is simply N, so I know that this N is going to be perpendicular to both N1 as well as N2. Is it okay?
Yes.
Fine. So it is the same information as this, isn't it? So that means the direction of this N and direction of L must be the same, isn't it? Right? So, I mean, they are going to have the same direction ratios. Fine? Okay? So, what we are going to do, we are going to find out the and so this I can write as ij k, then 1 1 1 1 minus 2 3. So this is equal to 3 plus 2. This is 5, right? Then 3 minus 1, that is 2. So this is minus 2j minus 2 minus 1, that is minus 3k. Right? So we have found out this. So basically what we have found out? We have found out a vector which is parallel to the straight line. Okay? So that means we have found out B. The component of B is 5 minus 2 minus 3. Okay? Now we have to find out a point on that line. Okay, so what we are going to do, see, I'm going to assume that this line, it intersects the xy plane. Okay, so if it intersects the xy plane, then what it must have? The j component. It intersects at the point xyz. So then j component must be 0, right? But before that, you have to make sure that this actually intersects the xy. Okay, how we can find out that if this line is not parallel to your xy plane, it is always going to intersect the xy plane, isn't it? Are you getting the point?
Yes.
Right? And from this, direction ratios, we can easily see that it is not so. Fine? Okay? Yes?
Yes.
Fine? Because just if I consider a line parallel to xy plane, so that means this is going to make angles what? This is going to make angles 0, 0 and pi by 2 0, 0 and pi by 2 with
Z axis.
those x's, right? So that means their direction ratios are going to be cos 0, cos 0, cos pi by 2, right? And obviously, these vector and this vector are not connected. Okay, fine. So, what we are going to do, say if you assume that, I mean, the straight line L, I want to find out the point of intersection of straight line L on xy plane. So then what we must have on xy plane, I must have x plus y equal to 1 and x minus 2y equal to 1, right? From the equation of these planes. Okay, fine. And from here, if you subtract the second from the first, then you are going to get 3y equal to 0, right?
Yes.
So that means y equal to 0. So if y equal to 0, x equal to 1. So I have found out a point 1, 0, 0 on that line L. Okay, and therefore the symmetric equation of that straight line is going to be given by your x minus 1 by 5, y minus 0, y minus 2 equal to z minus 0 by minus plus 0. Okay, this is what it is. So, yes.
XY plane. It is only on XY plane.
Yeah, I have taken it in XY plane. Yes, you can think about taking it in Y also.
Okay.
Y and Z also.
So we have to fix it first.
You have to what?
Fix it first, because if the intersection.
Yeah, you have to fix it first, huh? But you have to make sure from here. So from here it is obvious.
Okay.
From here it is obvious. Okay.
So we are fixing it because of that. We just know that the intersection is going to be the line. So that is why we are just fixing it.
We are fixing it because it is easier for us. It eliminates one variable, so that we can solve two equations, two unknowns from two equations. That is the point.
Okay.
That is the point. That is the idea. Okay, fine. Yeah. But again, remember, in that case, this is going to be entirely different. Okay, this, I mean, the A, B, C, the value of the deviation ratio, they are going to be the same. But the numerator, the symmetric equation, they are going to be completely different. Okay, fine.
Yes, sir.
So I think I am going to stop the recording here. So in my next class, I am going to do vector function and space curves. Okay. So I'll be really going towards your vector calculus from my next class. Okay. So thank you for bearing with me.